Chapter 3.4 is going to be just additional topics in probability. So there's going to be a couple main things we're going to be doing. We're going to be doing permutations and combinations and their formulas for them. For permutations, we'll start with these. There's going to be 3 different types of permutations. There's going to be essentially one type of combination that we'll do last. So for permutations, all a permutation is an ordered arrangement of objects. So the key word there is ordered. So the number of different permutations of n objects. So if we have n number of objects or items or whatever, if we want to figure out how many different ways there are to put them in order, there are n factorial different ways to put n objects in order. So that's n exclamation point, that means n factorial. And just like I mentioned, order matters for permutations. So if you've never seen a factorial before, n factorial, it's pretty simple to calculate. You multiply the number n, and then you multiply it by 1 less than that, and then you multiply it by 2 less than that, and you keep on going until you get to 1. So the formula for it's pretty easy. You just multiply by the number and keep on multiplying 1 less than that until you get to 1. So this is essentially the fundamental counting principle. But let's do some examples so we are comfortable calculating this. So for the first one, let's just do 1 factorial. So 1 factorial is actually just 1, so that one's pretty easy. 2 factorial is 2 times 1, so that's 2. 3 factorial is 3 times 2 times 1, so 6. So you can probably see that you don't really need to write the 1 because multiplying by 1 doesn't change anything. And do a couple more. 4 factorial is 4 times 3 times 2 times 1, which is 24. 5 factorial is going to be 5 times 4 times 3 times 2 times 1. This is going to be 120. And we'll stop there. Hopefully you can you get an idea of what's going on with this factorial now. So something to consider here. What if we have 0 factorial? So 0 factorial, you probably are thinking, hey, that is equal to 0, but it's not. 0 factorial is actually equal to 1. So since a factorial conceptually tells us how many different ways we can arrange that number of objects, 0 factorial, that's saying we have 0 objects. So we can arrange 0 objects one way, and that's just not having any objects. So conceptually it's a little bit odd, but just kind of know that 0 factorial equals 1 for now. There's also a button on the calculator. If you, depending on what kind of calculator you have, it might say PRB on it, and then these formulas will be under that button. So let's do an example. How many different ways can we arrange 5 books on a shelf? So we have 5 different books on a shelf. We want to see how many different ways we could possibly arrange them. That is just going to be 5 because the 5 books, factorial. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120 ways. So next example here we have, say there are 3 Olympic teams, the USA, Sweden, and Canada. We want to know how many different standings are possible for first, second, and third place with these 3 teams. So let's write down these possible outcomes. So for these, I'm going to go back up here. Obviously, order matters because we are literally putting things in order here. Let's get in the habit of just deciding if order matters. So for this one, we're talking about first, second, and third place, so clearly order matters. The reason is when we get to combinations, it's going to be a little bit different. So what I'm going to do here before we actually just do the little formula, I'm going to write down all the possible combinations. Or possible outcomes, rather. So I'm going to pause it and fill in all of these outcomes. Okay, so I filled out every possible outcome with these 3 different countries coming in first, second, and third place. So either the USA can come in first, Canada second, Sweden third. That's one option. USA first, Sweden second, Canada third. That's the second option. And then you can kind of read through those other options. So we can see that there's 6 possible outcomes here. So if we didn't want to write out all these outcomes, which is all the outcomes in the whole entire sample space here, we would say there's 3 different teams, 3 different standings, first, second, third. That's going to be 3 factorial, which is 3 times 2 times 1, which is 6 total outcomes. Okay, so that's obviously a lot shorter, so we're going to do it that way rather than write everything out. So now something that's pretty similar, but just a little bit different. So in the previous thing that we did when we were doing n factorial, we had n number of objects and we were putting them in order. And that n factorial told us how many different ways we could put them in order. So instead of choosing all of the objects, instead of choosing all of the n objects and putting them in order, we're going to choose a certain amount of them, but not all of them. So we're going to choose r number of objects out of n number of objects and put them in order. So the formula is going to look a little bit different here. So this formula, it just says permutations of n objects taken r at a time. This formula tells us how many different ways we can put r objects in order out of total of n different objects. So here's the formula. It's NPR, so we can see those 2 little subscripts next to the P for permutation, obviously. It equals n factorial divided by n minus r and then factorial. So you have to subtract the n minus r and then do the factorial for it. So let's kind of take a look at something here. Let's say we took a look at NPN. Let's think about what that means before we calculate this. So NPN means we are taking n number of objects out of the total number of n objects. So that means we're taking all of the objects and putting them in order. So that's actually what we just did, right? We took n objects and we put them in order. So let's see what happens when we use the formula and do that. So this is going to be n factorial over n minus r factorial. The r here is n, so it's n minus n factorial. This is n factorial divided by n minus n is 0, so that's 0 factorial. We know that 0 factorial is equal to 1, so this whole thing just equals n factorial. So technically that formula on the first page, n factorial, is just a simplified version of this formula. So let's do a couple of these by hand. There is a button in the calculator. Once again, it depends on what kind of calculator you have. A lot of them, it's still behind that. If you click the button that says PRB, it should be in that button. So let's evaluate 4P2. And let's conceptually actually think about what this means too. So 4P2, this means that we have 4 total objects, and we're taking 2 of them, and we're taking the 2 of them and we're putting them in order. So 4P2 is going to tell us how many different ways we can pick 2 objects out of 4 objects and place them in order. So let's calculate this. It's going to be n factorial divided by n minus r factorial. And then we have to simplify. That's 4 factorial over 2 factorial. So what I'm going to do here is I'm going to write this one out. We'll see a little bit of a shortcut. 4 factorial is 4 times 3 times 2 times 1. 2 factorial is 2 times 1. What is always going to happen here? You can always cancel out that denominator with part of that numerator. So the 2 times 1 cancels. So we're left with 4 times 3, which is just 12. So what this means is that there are 12 different ways. 12 different ways we can pick 2 objects out of 4 objects and place them in order. So let's do another one. So let's do 5P1. So this is saying how many different ways can we pick 1 object out of 5 objects and put them in order. So this is going to be 5 factorial, just using the formula, over 5 minus 1 factorial equals 5 factorial over 4 factorial. So this is going to be 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1. Once again, 4 times 3 times 2 times 1. Numerator and denominator are being multiplied, so they cancel, and we're just left with 5. So that means there are 5 different ways that we can pick one object out of 5 objects and put them in order, which should make sense because we're only picking one at a time. There's only one way to put one thing in order because it's just one thing. So all this means is at one at a time, we're picking one object out of the 5. So there's just 5 different objects to pick, essentially. Okay, so let's do this last one here, and then we'll move on to a word problem example. So 7p3, so 7 factorial over 7 minus 3 factorial. That's 7 factorial over 4 factorial. So I'm going to write this one a little bit different. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. 4 times 3 times 2 times 1 is the same as 4 factorial, right? So if we write it like that, we don't have to change that denominator. We don't have to expand it. So we can just cancel the 4 factorials. We're left with 7 times 6 times 5, which is just 210. Okay, so for example, let's find the number of ways forming a 4-digit code which no digit is repeated. So this order matters because it's a password. So hopefully we're looking at this problem and we're thinking, well, we've done ones like these before, which is true. This is just the fundamental counting principle. So we know we're going to be doing this formula because we're in this part of the notes. So it's NPR equals n factorial over n minus r factorial. So the reason why we also know that we're using this formula, we're going to have a total number of options, which is n, and we're picking r of them. So it's a little bit tricky. The n here is 10. It's the number of digits. So we have 10 digits to choose from, and we're doing a 4-digit code. So that means r is going to be 4. So it's going to be, we're evaluating 10PR. Or 10p4, sorry, 10p4. So plugging this in, it's going to be 10 factorial over 10 minus 4 factorial. That's 10 factorial over 6 factorial. I'm going to do the shortcut way again like I did in the last example. 10 factorial is 10 times 9 times 8 times 7. Everything after that is 6 factorial. So the 6 factorials cancel, and we are left with 10 times 9 times 8 times 7, which is 5,040. So if we were doing this the way that we did it before with the fundamental counting principle, we would say, okay, we have 4 digits. We have 10 options for the first digit. We can't repeat any digits, so we have 9 for the second, 8 for the third, and 7 for the fourth. Taking a look at what this formula simplified to, 10 times 9 times 8 times 7, that is the fundamental counting principle right there. Okay, next problem. So 43 cars are at a Daytona race, and we want to know how many different ways can they place first, second, and third. So I'm just underlining some of the important information. So clearly the order matters because we're talking about a race coming in first place, second place, third place. So the formula NPR equals n factorial over n minus r factorial. So the n here, the n is the total number of cars in this case, which is 43. It's the total number of options that we're picking from. The r is how many we're taking and putting in order. That's first place, second place, and third place. That's going to be 3. So we're looking for 43 P3, which is going to be 43 factorial over 43 minus 3 factorial. So that's 43 factorial over 40 factorial. So this is one where you're going to want to use that shortcut where you're doing 43 times 42 times 41 times the rest after that is 40 factorial, all divided by 40 factorial, because you don't want to have to write out all the way to 1. So cancel, cancel. 43 times 42 times 41, that's going to equal 74,046. So these numbers tend to be a lot bigger than you might just guess if you were guessing. If you have 43 cars at a race and you're trying to figure out how many ways possible can they come in first, second, and third place, your initial guess might not be this big, but that's actually the answer. There's 74,046 different possibilities for coming in first, second, and third place. Okay, so far we've done two of the formulas, two concepts, which were kind of the same thing. So we did n factorial, which is how many different ways we can group n objects or arrange n objects in order. Then we did npr, which is how many ways we can choose r objects out of n objects and put them in order. And then for the last type of permutation formula, this is distinguishable permutations. So the idea for this is we may want to order a group of n objects where some of them are the same. So we're going to have some of the same objects. So let's say we have this example, A, B, B, and C. So before, when we were doing this, if they said how many different ways can we arrange those in order, we would say, well, there's 7 different letters there. There's 7 different objects. So that we would say that there's 7 factorial different ways that we could arrange them in order. There is repetition here in this these set of letters though, so not all permutations are going to be distinguishable. So that means if we have like that first A and that second A, if we flip-flopped the order for that, technically it would be a different permutation, but it wouldn't look any different. So it wouldn't be distinguishable. So since some of these objects repeat themselves, this formula that we're going to use is going to divide off the permutations that are not distinguishable. So it's going to seem a little confusing. The example should clear it up though with the formula here. The number of distinguishable permutations of n objects, so n total objects, where n sub 1 are of one type that repeat themselves, n sub 2 are another type that repeat themselves, and so on, is going to be n factorial divided by n sub 1 factorial times n sub 2 factorial, and then you keep on multiplying by how many different objects there are. Okay, so let's do an example so that formula can get cleared up, hopefully. So let's find the number of distinguishable permutations for A, B, B, and C. So first, I'm going to just count how many objects we have. We have 7. So n equals 7. So using this formula, we have 3 different types of objects. We have A's. Oops, we have A's. We have B's, and we have C's. So what I'm going to do here is I'm going to say n sub 1 is going to equal the number of A's, which is 4. N sub 2 is the number of C's, or number of B's, which is 2. And n sub 3 is going to be the number of C's, which is just 1. Okay, so something to keep in mind here. Put a little note. When you're adding all of these up, n1 plus n2 plus n3, that should always equal n, which it does. 4 plus 2 plus 1 equals 7. So doing this formula, it's going to be the formula right up here. It's going to be n factorial over n sub 1 factorial times n sub 2 factorial times n sub 3 factorial. So we just have to plug everything in. So n was 7. That's 7 factorial. And n sub 1 is 4, so 4 factorial times 2 factorial times 1 factorial. So this is going to be 7. So if you're doing these by hand, you can cancel off the largest factorial in the denominator using the numerator. 7 factorial can be written as 7 times 6 times 5 times 4 factorial, all divided by 4 factorial, and then 2 factorial is 2 times 1, and then 1 factorial is just 1, so I'm not even going to write it. So I wrote it like this so we can cancel off those 4 factorials. 7 times 6 times 5 divided by 2 is 105. So there's 105 different distinguishable permutations for that arrangement of letters. Okay, next example. So there are 12 houses on a street. There's 6 one-story houses, 4 two-story houses, and 2 split-level houses. We want to know how many distinguishable ways can houses be arranged. So let's underline some important information. There's 12 total houses, so that means n equals 12. 6 are of one type, 4 are of another type, and 2 are of a third type. So n sub 1 is going to be the number of one-story houses, which is 6. N sub 2, number of two-story houses, which is 4. N sub 3, number of split level, which is 2. So using the formula here, it's going to be n factorial over n sub 1 factorial times n sub 2 factorial times n sub 3 factorial. So it's not always going to be 3 different types of objects, but in this case it is again. So it's going to be 12 factorial over 6 factorial times 4 factorial times 2 factorial. So I'll leave this to you guys to try to solve this on your own. This is going to end up being 13,860. So there's 13,860 different ways for this. Let's do one more example. So how many distinguishable ways can the word banana be arranged? So same concept here. So n, the total number of objects, is 6. There's 6 letters here in banana. N sub 1, I'm going to let this be the number of B's, which is 1. N sub 2 is going to be the number of A's, which is 1, 2, 3. And n sub 3 is the number of n's, which is 1, 2. So this is going to be n factorial over n sub 1 factorial times n sub 2 factorial times n sub 3 factorial. So it's going to be 6 factorial over 1 factorial times 3 factorial times 2 factorial, which will end up being 60. So there's 60 distinguishable permutations for the word banana. Okay, so that puts us to 3 different types of permutations so far, 3 different formulas. So for the last thing, we're going to do combinations. So for combinations is going to be, before I get into the actual definition, it's when order does not matter. So anytime order matters, it is a permutation. Anytime order does not matter, it is a combination. So the idea for combinations, it's going to sound pretty similar to permutations. It's how many different ways we can choose R objects out of N objects. And that's it. So notice the order does not matter here. Permutations, we said for NPR, we said it's the amount of ways we can choose R objects out of N objects and put them in order. For combinations, it's the number of ways we can choose R objects out of N objects, where the order does not matter. So the formula for this is going to be NCR. So the way that we can read this is N choose R. So it's essentially saying we have N objects and we're choosing R of them. It's going to equal N factorial divided by N minus R factorial times r factorial. So notice that is the same exact thing as the permutation formula, except for the r factorial is new for the combination formula. So the reason why that r is there, so that's this one right here that I'm talking about, everything other than that is the permutation formula. What that's doing is it's dividing off the number of permutations for r, which is saying the order does not matter. So let's do some examples here by hand. This is also in the calculator. You can use the button to help you. So 8 choose R. So I'm going to be reading this as choose instead of C. You can say 8 CR. I'm going to say 8 choose R. So this is going to be 8 factorial, using the formula from above, divided by 8 minus 3 factorial times 3 factorial. It's going to be 8 factorial over 5 factorial times 3 factorial. So doing these by hand, you can cancel that largest factorial in the denominator using the numerator. So I'm going to rewrite the numerator as 8 times 7 times 6 times 5 factorial, because that's the biggest one in the denominator. And then I'm going to write 3 factorial as 3 times 2 times 1. So I wrote it this way because we can cancel off the 5 factorial. So it's 8 times 7 times 6 divided by 3 times 2 times 1 is going to equal 56. So what does this mean? This means there are 56 ways we can choose 3 objects out of 8 objects. For 10, choose 10. So this is saying how many different ways can we pick 10 objects from 10 objects. So think about that while I'm kind of writing down this formula here. If we have 10 objects and we're picking 10 objects out, how many different ways can we do that? So plugging these values into the formula, 10 factorial over 10 minus 10 is 0, 0 factorial times 10 factorial. 0 factorial is equal to 1. The 10 factorials cancel off. So this is actually just equal to 1 over 1, which is just 1. Which should make sense because if we have 10 objects and we're choosing all 10 of them, there should be one way to do it, and that's just by grabbing all 10 of them once. So in general here, if we have n see n, n choose n, where those are the same values, it's always going to equal 1. It's not anything that you technically need to memorize because you could always do this little, do the example, do the problem. Next one with 5 choose 1. So doing 5 choose 1, plugging these values in the formula. So this is saying how many different ways can we pick one object out of 5 objects. So once again, try to maybe think about this before we evaluate it. So this is going to be 5 factorial over 4 factorial times 1 factorial. This is going to be 1 factorial is equal to 1. 5 factorial we can rewrite as 5 times 4 factorial, and the only reason I did that was to cancel the 4 factorial. So this is just going to be equal to 5, which once again hopefully makes sense. If we have 5 objects and we're seeing how many different ways we could choose one of them, that's just taking each one of those 5 objects, which is a total of 5 different ways to do it. So in general, if we have n choose 1, that's going to equal n. Okay, let's do more of a word problem here. So a 3-person committee wants to be formed for a company out of 20 employees. We want to know how many different ways we can form this committee. So just by looking at this, we should be able to see that the order does not matter. So order does not matter, meaning this is just going to be a 3-person committee out of 20. All of these people are exactly the same, essentially. They're just one of the 3 in a committee. So we know this is going to be a combination because the order doesn't matter. The n is going to be the total number, which is 20, and the R is going to be 3, the number that we're picking out. So we're going to do NCR, which is n factorial over n minus r factorial times r factorial. So this is 20, choose 3. How many different ways can we choose 3 people from 20 people? This is going to be 20 factorial over 20 minus 3 factorial times 3 factorial. And I'll simplify the parentheses. That's going to be 20 factorial over 17 factorial times 3 factorial. I recommend you guys trying this by yourself. To finish this off, you end up getting 1,140. So once again, that's pretty big number, pretty big amount of possibilities for choosing 3 people out of 20 people. Okay, next one, a football team wants to elect 4 captains for their offense, which consists of 11 players. We want to know how many different ways can they do this. So 4 captains out of 11. So order does not matter. All of these captains are the same. They're just one of 4 captains. So order does not matter. So this means we're doing a combination. So n is the total amount, which is 11. R is going to be 4. So we're doing n choose r. N factorial over n minus r factorial times r factorial. So we're going to do 11 choose 4, which is 11 factorial over 11 minus 4 factorial times 4 factorial. So I'll just simplify the parentheses and get 11 factorial over 7 factorial times 4 factorial. And simplifying this, we will end up getting 330. Okay, so that is permutations and combinations. So that's 3 formulas for permutations and the 1 formula for combinations. So for applications and probability, we're going to be doing probability-based questions here, except we're going to be integrating these ideas that we just did into this. So for example, a student board consists of 17 members. 3 members serve as the chair, secretary, and treasurer. So it's 3 members. What's the probability of selecting 3 members at random who currently hold those positions? So you walk into a room, there's 17 people there, and you want to know what's the probability of correctly choosing who the chair is, who the secretary is, and who the treasurer is. So one thing to realize first here is that the order actually matters for this one. So the order matters because each choice represents a different position. So the chair is not the same as the secretary, which is not the same as the treasurer. So since the order matters, this is going to be a permutation. So setting this up, we know that n is going to be 17. R is going to be 3. So this is going to be NPR, which is n factorial over n minus r factorial. So it's 17 P3, 17 factorial over 17 minus 3 factorial. That's 17 factorial over 14 factorial, which is 17 times 16 times 15, which is 4,080. So what this means, what we just found, if there's 4,080 different ways the positions can be filled. So there's 4,080 different ways that you can guess the positions. So now answering the question here, we did the hard part. We want to know what's the probability of walking into the room and randomly selecting the correct people who belong to those positions. So there's only one correct way to fill the positions. You can only pick the one correct chair, one correct secretary, and one correct treasurer. So the probability of selecting the 3 correct is going to equal 1 out of 4,080. So the 1 is because of what I just said. There's only one correct way. So there's one correct way to choose those positions. And the 4,080 is what we just found. That is the number of different ways the position can be filled. Okay, so this is actually the multiplication rule, for the other way to think of it. The multiplication rule would be, in order to choose the probability of choosing all three correct, the probability of choosing the first one correct is 1 out of 17. The probability of choosing the second correct is 1 out of 16. The probability of choosing the third correct is 1 out of 15. If you multiplied those three fractions together, you'd end up getting the same thing. Let's do one more here. So find the probability of being dealt 5 diamonds from a deck of 52 cards. Okay, so we're being dealt 5 cards. We want the probability that they are all diamonds. So it's important to note here that the order does not matter. There's no order involved in this. So if order does not matter, this is a combination. Okay, so what we're going to be doing is the probability of getting 5 diamonds. That's going to equal the number of ways to choose 5 diamonds divided by the number of ways to choose 5 cards. Okay, so hopefully that makes sense. It's the number of ways that we can get our desired outcome. Oops. The number of ways we can get our desired outcome divided by the total number of outcomes. That's all that is. We've done that before. So the number of ways to choose 5 diamonds, there are 13 diamonds and we're trying to choose 5 of them. That's going to be 13 choose 5. The number of ways to choose 5 cards total, there's 52 cards. So it's going to be 52 choose 5. So either evaluate this by hand, plug those into the calculator separately. You're going to end up with 1,287 divided by 2,598,960. So dividing this, you get about 0.0005. So there's about a 0.05% chance of getting 5 diamonds in a row from a deck of 52 cards. So the other way to do this, once again, is the multiplication rule, which we actually did several times already. You would say the probability of the first one being a diamond is 13 out of 52. Second one being a diamond is 12 out of 51. Third one being a diamond, 11 out of 50. Fourth one being a diamond, 10 out of 49. Fifth one being a diamond, 9 out of 48. You multiply all those together, you get the exact same thing. So there's usually going to be multiple ways to do these. But this one, I want to do these ones this way because they use combinations and permutations. Okay, so that is it for chapter 3.4.